Alright everyone, it's Jeremy again. I'm back. I'm doing another tutorial for you guys in SolidWorks and HSMWorks, and we're going to actually start with CAM and Toolpaths today. And so I'm going to go through the process of actually camming a part, give you guys the basics that you need to know to get started. The idea is not that you're going to have a perfectly cammed part when you work on your parts, but it's that you have an idea of what's happening and you do your best to start so that me and others who are experienced are able to jump in and give you help, right? So if you come to me with an attempt, I can be like, well, you're right here and I'll help you here and you're going the right direction. But if you come to me with nothing at all, you're not invested into the part that you're making. So I'm excited to get started and to see what you guys take out of this. Hit me up with any questions on Slack as usual, and we'll dive right in. And so as I said last time, you should have done my previous tutorial on tool libraries and post processors, and those should be imported in. And now we're going to go into the actual CAM workspace. Remember, not SolidWorks CAM, but HSMWorks. And that's just labeled as CAM. And we're actually going to start by making a job. These are all of the operations that are possible, but none of those can do anything unless they're placed inside of a job. And so the foundation of a job is it tells you what the material you're starting with is. It says your coordinate system, which, as we discussed in my presentation to you all before quarantine, was basically where the machine measures from. And this center is already set to the center top of the stock, right? And the stock is already set to a fixed sized box. It's just relatively slightly larger. A relative sized box. And that information is essential because it tells the machine what it needs to cut, so when to expect material and to start cutting. And it also tells the machine where to start from and where zero is. And so the first thing we'll do is we're going to say milling. If you do turning or mill turn, that's straight up for turning. And this is kind of a mess because it's trying to actually turn a part, and that's not going to work because it's not a part for lathe. So we'll do milling. We have our model, and we'll do a fixed sized box. Relative sized box is not really necessary unless you're have stock left over and you want to just face a pre-sized block, that kind of thing. Really, you want it to match the exact dimensions of your stock that you picked up from downstairs. So say I get a piece that's 10 inches in X, right? That reflects there, and that's absurd. So we'll do something like 5. 5 inches is reasonable, right? And then Y will do 3. And then height, we'll do 1 inch, right? And based on these dimensions, you can tell that my coordinate system is already correct. But if I had to, I can change that coordinate system. You'll notice it says centered on Z-axis. That means that there's an inch of material and it places the model right in the middle. But we really only need to face off a small amount on top to make sure that we have a smooth surface. So we actually want to offset it from the top, and then our depth of cut is 0.05 inches. My bad, sorry. My depth of cut is 0.05 inches, which means I want to offset it from the top by 0.05 inches. That means all we need is one single pass offset from the top to make a smooth surface, and it doesn't waste time or material trying to mill that away, right? So in our initial setup, we want as much as possible to be able to clamp down here and hold the part while we work. So in some cases, it might actually be better to have a 2-inch block, right? Because then I can come saw it off later. But for now, we're going to do 1 inch for the simplicity of this tutorial. And then we won't be doing fixturing. Right now it says use stock and orientation. We want to leave it in the top center, right? That's the center of the block so we can probe it. But we want to make sure we check our orientation. So if I want my Z-axis to be towards us now, I just click this face and now the Z-axis in blue comes out of it. But we still want it to be as usual. So we want our Z-axis up, and then we want our X-axis to be to the right, and that's already the case, right? If I flip direction, right? There you go. That's another option as well. And using the right-hand rule, you stick out your pointer, middle, and thumb finger on your right hand. Make like a T so they're all perpendicular. In a proper machine, point the middle finger up, and your thumb on your right hand is pointing in positive X, and this is if you're staring at the front of the machine. Your pointer finger is pointing in positive Y, and your middle finger is pointing in positive Z. And so this is how you know right away what the machine is doing. So if I were to stare in front of the machine, the part would look like this to me. But I want to see what it's doing in the back, and this isn't super necessary, so I'll just reverse the X-axis. And now, once again, this is how you'd see it in the machine. And so that is how you set up your stock and you set up your job. Once I have my stock and my job done, right, I'm going to decrease the size of this box to save, quote, machining time, 2.5, right? Hit OK. Now I can begin to work on machining. And I can create infinite number of jobs, and I post them all as separate files to machine from, right? So I can do one job for one bit of the part, another job for another bit of the part. And I've done this before on parts where I have extremely complex and precise parts that I want to check each time or reprobe. But for now, we have a job, so we can start. We'll start with the simplest bit, which is going to be our drilling, or our facing. Sorry, not our drilling. We'll face. Facing is a 2D operation. When you select facing, you need to give it a tool, and we use shell mills for facing because they remove material the fastest. You have your libraries now. We're going to use a shell mill, and we're going to go look for KCN because we're doing aluminum for non-ferrous N. We don't want an N mill, that takes forever, so we're looking for KCN shell mills, 2 inches. 2 inches in diameter is the largest. That'll be the fastest. You can see it modeled here. So next thing is these feeds and speeds. This is already given to you, and it's perfect. It's from Bechtel's tool library, so ignore it. If you're using a machine with coolant that shoots through the tool, we'll select through tool, but for now we're really just doing flood, and that's a case-by-case basis. We don't need to select stock contours. A facing operation automatically selects the closest surface to face down to. You don't need to change anything here except for these two heights, which says 0.5 inches from stock top for both. What this does is it tells it where to move to each time it changes a position. So if I have multiple depths or I'm cutting and I'm going to different places, I need to reposition safely so it'll go up half an inch so it doesn't hit anything. That is your heights bar. This is the same for almost every operation. Next, we look at our step over, step down, and tolerances. You need to think about your step over. So what are we doing for a step over? This is how far over it cuts each time. So we want it to be 2/3. So 0.666, or just simply 60% is easiest, times the diameter of the tool, 2 inches. That's your rule of thumb for shell mills. Not for end mills. You'll snap an end mill in a heartbeat. That's it. Don't change anything else. Multiple depths. If you're facing down very far, you want to step down 0.05 inches each time. But since our stock above the part there is only 0.05 or 0.5 inches, or 0.05 inches, we shouldn't have a problem. Let me be 100 million percent. Yeah, it's 0.05 inches. So we don't need multiple depths. And you can verify that just by going back in and editing. Once again, you can change all of this as you go and as you figure out what's happening. Now that we have our job with our facing operation, you'll see that there's different stuff about rapids, extensions. Don't change any of this. It's fine. If we have issues, me or an experienced TA will change it on a case-by-case basis. Be aware that when you go into the BIDC, this is different than Fusion in a graphical interface perspective and in some features, but not in a functionality perspective. So all of these commands are the same. So instead of knowing exactly what each thing does and what it's supposed to look like when you're working, I prefer you know where things are. So if someone says, what the heck is the heights tab? You can go, hey, here it is. What do you do in Fusion? And I'll do it here for you. That way you guys are able to work in SolidWorks and work with the instructions they'll give you that's related to a Fusion project, as long as you know where stuff is, because stuff is a little bit different. And we'll talk about that more in a little bit as we get into more complex work. So now that we have a facing operation, we will have a theoretically smooth surface. So I can select my job and simulate the whole thing. And when I do and enable stock, you'll see that it's going to come in. It's going to take 60% of the tool. And it's going to cut back and forth. Come on. There we are. It's just super slow. It's going to go back and forth facing down the part. Perfect. And now you can see these lines showing that we are indeed at the surface of the part. Next, we'll drill. I prefer to do interior operations before exterior operations when it's a matter of rigidity. In this case, this part, it does not matter. But for a part that's very thin or that needs a lot of material removed and holes drilled, you should drill your holes when the thing's a big block and you face down to that surface, because it means that it's rigid and it's not going to flex and it's not going to vibrate. So the best way to remove resonance and ensure a good surface finish and high quality and tolerances is to make sure that your part is as rigid as possible for as long as possible. So if I'm milling away material, I want to order my operations in a way that I'm keeping my part rigid. Because if I were to mill around this tiny hole and say I have to mill all the way around here until it's just a tiny wall and then drill my hole, that's kind of silly. It's not that stable. There might be some issues, especially if you're putting high machining loads on it. So I'd rather drill first. So I'm going to do that. I'm going to go to my drilling operations. Drill wizard, don't use, just use drill. It's better to know what's happening than to try to have an AI or a really bad computer do it for you. Now we're going to find a drill for our hole. In our dimensions, we know this is a number 1032 hole. We don't have taps in this library yet, and that's something we'll encounter later, and I'll make a video about it if need be, but for now, we're going to look at the drills tab in the end section once again. These are this perfectly sized drill because you drill underneath the hole diameter, then you tap it later, and that tapping expands it. So I find the 1032 drill that's perfectly sized, and then it's going to drill just the right amount so that when I tap later, we reach the proper dimensions. Once again, you could pick any size drill, and the way that drills are defined, it doesn't matter about what's actually in the physical part in CAM. And in CAD, it just looks for the center line and the depth. So if you choose the wrong drill, it's not going to tell you you're wrong. It's just going to do the wrong thing. So be sure you're careful about that. Spindle speed, surface speed, and retract are okay. We like to retract at 300 inches a minute. That's just a general rule of thumb. The longer we stay down, the more rubbing and the more damage to the tool if heat builds up or something bad happens. Next, we're going to select a single hole. These are the holes we want. And we're going to select the same diameter. This saves you a lot of time, right? Because now we just do all of it. And then we're also going to look at our depths now. Once again, 1/2 inch from stock top. That's our always rule of thumb. If we need to speed stuff up, we'll look at it at a case-by-case basis, but this doesn't add all that much time for the safety you're getting. Now, an important thing to think about is that a tool has a chamfer, right? So look at this, the ring and then the green line. The green line and this highlighted hole is the tip of the tool, whereas the ring is the chamfer. If we wanted to go all the way down to that chamfer, say tapping or have that depth, we want to drill tip through bottom. That's actually going to bring down, you'll see that green line shifts right here. That's going to bring down the tip and the chamfer to the edge of the bottom of our hole, meaning that our hole is going to be properly dimensioned. It's going to have a chamfer. Very rarely do we end up with holes that are perfectly square at the bottom. There's no real need to. So we'll go ahead and drill tip through bottom. That'll give us the ideal dimensions of what we want. And then now, if you wanted to have it go through like all the way through, you could do that, but we don't need to do that. And so we're good now. Our hole matches. I can hit OK. If we check the rapid cycle, right, if I want to change to a PEC drill, if someone says that, or right tapping, reaming, boring, thread milling, all this fancy stuff you can. But for carbide drills with coolant, we rapid out drill. We never PEC drill. For high-speed steel jobber drills, those are those little cheap high-speed steel drills, you always PEC drill because they can't handle the load. They're not cutting as well. Remember, the tip of the drill is the only thing doing the work. The flutes are just there to evacuate the chips. Now we have our drilling cycle, and if I simulated this, you'd see the same thing. But now we're about to diverge, right? So I'm going to create two different jobs here, and I can do that by copying and pasting, Control-C and Control-V. I'm taking two different approaches to the next part of the operation, which is adaptive. First, I'm going to do a 2D adaptive, right? 2D and 3D are fundamentally different. 2D is selection-based, 3D is geometry-based. 3D looks for physical features on the part and then machines around them. 2D milling will do what you say and neglect everything around it. So if I say 2D adaptive, always adaptive, then contour, right? Because adaptive is a highly enhanced machining operation trying to clear material as fast as possible. If I turn off machine cavities, it's going to try to machine around the outside of this. If I turn it on, it's going to do the inside regardless of what I select. It's doing this contour down to this depth, and all it's thinking about is what's inside this line. So if there's a piece hanging out in the middle that I do not select, it'll machine right through it. So you got to be very careful that what you see is what you get, and that's why simulation is important. Rest machining is also somewhat important if you have a lot of previous operations, but in this case, it's not a problem. Retract heights, you guys know what to do. If I was in a room, I'd ask you and you'd respond, and we'd have a good laugh, or no one would respond, and I'd feel depressed, but you've just said to yourself 1/2 inch, and then I say you're right, good job. Now here's what's important now is our engagement. So optimal load of the tool for an end mill is 7%, 0.07 times the diameter of the tool, right? And I forgot what tool I selected, right? I didn't select a tool yet. We're going to start with a 1/2 inch end mill and hit select, right? Because that's our number one choice. That's the best for the job. It's the easiest to think about. 0.07 times 0.5. And then we want to make sure we're not using too much, and it's 0.9 times the flute length. Well, what's the flute length? I have to look in my library. It says 1 1/4 inch. So 1.25. So 0.9 times 1.25. This is the best way to machine. Low radial engagement, high axial engagement is the fastest way to remove material for an adaptive operation. Stock to leave. We want to leave room to finish, right? We want to make a nice surface finish because an adaptive is rough. We don't worry about the bottom because since it's not surfacing, moving up and down, the bottom's going to be flat no matter what, right? If I take my finger and drag it across the desk, no matter what happens on the sides, the tip is always in contact. I'm going to take 0 inches axially, 0.02 inches radially, and that's fine for now. You could step it up, but a lower stock to leave is fine. Now, that's all you need to do. Remember, always set your engagement, so your optimal load. Always set, what's this here? Minimum cutting radius. We want to drop that so it's actually below what we're doing. Something decent, that's fine. And then multiple depths, state your flute length. These two things, and then sometimes this, are important. Don't worry about linking. Hit check. It'll now generate a perfectly optimized toolpath to try to remove material as fast as possible, and you'll see that here. Well, what's the next thing we need to do? We need to take care of the outside. There's these two areas to think about. The hard part about the selection basis is that I don't have a selection for this pocket that goes all the way around and removes material. But I can select a contour and a depth separately. So I'm going to create a derived operation. This lets me keep my tool and my tool parameters exactly the same. So I don't have to worry about changing that engagement and that depth of cut anymore, and it keeps it the same. I just have to reselect. So I'm going to delete my selection, and I'm going to look at this outside bit. I'm going to say, whoa, here's a nice thing here. I want this outside edge, right? Because this outside edge is the perfect contour. I'm not going to go past this bottom bit because I have to hold on to my part. I don't have much room otherwise. So I'm going to machine down to here, and then I'm going to do this in another operation on the bottom. I need to think about how I'm holding the part when I'm machining. That's number one. I want to turn off machine cavities. Here's what's important. On Fusion, there's a red arrow that sits next to us. When you click the red arrow, it reverses inside-outside. If I click this now, it's going to machine inside. That's not what I want. I want the outside, so turn off machine cavities. If a TA tries to be like, why the heck is this not working? That's the red dot, that's the red arrow in Fusion that you have to click. Next, I'm going to go ahead and set my heights again. They're the same, right? Because I did it right. But my bottom height's going to change because my contour is the top. I want it to be a selection. I want it to go down to this depth. Now it's going to take this outline and put it down to that depth, if that makes sense. And these are all the same. I don't have to worry about changing it because I created a derived operation. Now I have two operations that take care of it all. This is 2D once again, remember? And now when I simulate, what's going to happen is it's going to face, it's going to drill, it's going to do all my wonderful work for me. And I'll turn on the stock so you can see. Drill, 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 drill. Helical down because the center of an end mill can't cut, as we talked about. And it's going to start working its way down. Low engagement, high feed rate. Low engagement, high feed rate. That's what this is for, and it's really good. So as it's working, it's cutting away the material as fast as it can. You'll notice something peculiar about the inside. There's these really large corner radiuses, and it's kind of sketching me out, right? Because if I take a tool and try to move along this line, that's going to be a really sudden and intense engagement. If I reach that, it might snap my tool. Well, let's think about why that is while we see the rest of it working on the outside. So it's going as fast as it can. Okay. And it's going to get rid of that pocket there. And once again, we run into that issue here. You'll see there's a lot of material left over. That's more than 0.02 inches. That'll snap my tool. What do I do? Well, here's the solution. We got to look at our part and think about it in context. If I have a 1/2 inch end mill and this is a circle of 0.4 inches, it's not going to fit in that radius, so it's going to get as close as it can. So if I evaluate and I go ahead and hit measure, and then check this, it says that its radius is 0.2 inches, not 0.25 inches like my tool, which means I can't reach this radius. What do? I simply pick a smaller tool. I look for a tool that'll solve my problem by fitting inside of these holes. So all I have to do is edit, and I got to change my parameters. Remember, there's a way to do tool parameters, but I'm not sure how to do that as clearly in SolidWorks as in Fusion. And I want a 3/8 inch flat KCN end mill. So when I select this, 3/8 inch will fit inside of this hole. I know because I've checked it out, but you can do the fundamental math, find the radius, and compare it. Now, all I got to think about is, okay, what's this? This is our tool diameter times 0.07. So it's 0.07 times 3/8, done. What's this? What's our depth of our tool, right? So I look at my tool, it says 3/4 flute length. So once again, it's 0.9 times 0.75, done. This is still below that. We'll make it 0.015 for fun, just something reasonably below and not too small, nothing smaller than 0.01, but still smaller than the proper engagement. And then I click back. Done, it's fixed. Do the same for the outside, right? They're not linked, so I can't ripple the effects over, which is why a lot of 2D adaptives is not as fun as a 3D adaptive. We'll talk about that in a second, right? And then once again, 0.07 times 3/8. Done. 0.9 times 0.75. And then all this is okay. We said, oh, let's make this smaller. It doesn't matter that much as long as it's a minimum engagement is smaller than the optimal, right? Because I can't have a minimum engagement larger than what's best. Then it just is pointless. Now we have our toolpaths. And then if I simulate this entire operation, right, we're going to look and we're going to see, whoa, oopsie daisy. There we go. There's going to be a nice even amount of material all the way through, right? It's fairly close to what's over here. It's all the same, right? And that's perfect. That's what we want. So now we're good. What's the final thing we have to do, right? We have to smooth this all out because an adaptive, you'll see, is rough. All these little lines leave little straight edges. See, this is a corner. This isn't rounded, right? It's not trying to round it. It's trying to move as quickly as possible in the least amount of code. Because if I try to do a perfect curve, it takes a crap ton of code. What do? I create a contour. I'm going to create a derived operation for the first one on the inside to finish the inside, right? This is going to keep the same selection. 2D contour. Done. Pretty much all I have to do. Don't change my feeds and speeds. My selection is the same. My heights are proper. The finishing passes doesn't need anything. If we have to do multiple depths, we can, but we don't need to, right? And there it is. There's a line that perfectly fits what's drawn here. Let's do the same for this other second operation, right? We're going to create a derived operation, 2D milling, contour. I'm not even going to check it now, but you would do that if you were working, right? It's going to do a perfect outline around the outside, and that's what we want. It's going to finish the work we started. If it works, right? And so let's look at it, see what's wrong. Why didn't it work? The tool is correct. The edge is correct. The selection is correct, and the depth is correct. Is it something to do with machine cavity? Let's look. Yeah, see now there's an arrow. Uh-oh, see that's the arrow I was talking about. What do? I reverse the arrow is what we want because it's thinking the inside when it contours. So I need to flip its direction. Reverse. Now it's on the outside. Problem solved. Right? If you don't see your toolpath, you got to think what's going on. And now when I simulate, it's gonna, oops, see, not as pretty as Fusion. Sorry, I had to shill. We'll get to the end of this operation here, and you'll see it's gonna make a final pass on everything. Oh no, it didn't. What went wrong? Well, when I created my derived operation, I didn't say, oh, what about the part that I left the same for stock to leave? Now it's not actually finishing, it's just tracing. I get rid of stock to leave, and now it's actually going to get rid of the rest of the material, right? It's going to move it 0.02 inches closer. So if I do that for all this, and once again, the rest of these settings in this menu are entirely contextual. If I run into an issue when I'm machining, I look into those to fix it, but not when I'm starting out. The more you mess with it, the more unexpected things might happen, right? And so now you'll see that there's a perfectly machined surface there. It's like glitching between rounded gray for the part and yellow, which means it's right on it, right? And so it's done. We've done everything. Now it's a completely machined part. All we have to do is tap it and take care of the backside, which we'll talk about in a second. Now we're going to approach this through the lens of a 3D adaptive. I can keep my contours the same because I still want to do a 2D contour. You don't want to do a 3D contour. I can copy and paste them and drag them into this next job. Let's make sure that it actually can lift them. Unfortunately, it's being silly. Delete. We'll try one more time. Inside, outside, copy, job, paste. There they are. Just regenerate them. And now, boom, our finishing operation's there. All that we have to do is rough adaptive clearing in a 3D adaptive. My tool is the same. My feeds and speeds may not be the right ones, but we'll fix it. Rest machining from previous operations, right? We don't want to waste time. In a selection basis, it's not a problem, but for a 3D adaptive, right, it's going to try to cut all this top part off unless we tell it that we've already done it. Previous operation. Retract and clearance. I'm going to ask you what's the proper height. You're going to say, oh, 0.5 inches, yay. You guys are picking up on that. Make sure it's stock, otherwise you're wasting time. We want to go all the way down, but not this far, right? Because if we go this far, we're going to cut our vise. So what do? Selection, that depth. That's it. Or that depth. They look like they're very much the same. We want to make sure we're getting all the way down. Optimal engagement, right? 0.07 times 3. Oops, see, typo. 3/8. Done. I'm going to do the same thing for optimal engagement. It needs to be smaller. 0.15 is fine for now, right? And then this is important. This is our maximum step down. It can't be any bigger than this. So what do? Remember, 0.9 times the flute length, right? Which is 3/4. Out of times there, syntax. Minimum step down just needs to be smaller than that, and that's fine. It doesn't matter. It won't be a problem. We want to make sure no axial stock to leave as usual. We want to machine by area, not by depth. That means it's going to complete this bit and then move to the outside, not hopping back and forth in a hopscotch pattern. And that doesn't matter too much. You can change that later, or a TA will help you. And now when I hit check, it's going to take a second, right? And it's doing it in the wrong job. I'll just move it over in a second. And since it used previous operations, it didn't have to cut anything. We'll put it back here now where it belongs. Generate. Now it's going to generate a toolpath, and it's taking a second, right? Because it's got to look at this and say, where's my geometry and where's not. There you go. It does the same exact thing, It just takes one less toolpath, right? And it's more succinct. It saves you a bit of time. And I like 3D adaptives a lot. It's just contextually you may have to make a decision. And when I run the toolpath and I simulate it, it does the exact same thing. There's no doubt. There's no question. It's exactly the same. So when we get to the end here, right, it'll show up with red marks if there's arrows as well, right? It's going to rough it out. It's going to finish it. We end up with the exact same result. There's not a problem at all. Now we just got to finish it, right? And I can just quickly do the rest of the work. So I'm just going to copy this job that I like. Control-C, Control-V, and then look inside of it and see that I got a facing operation, which I need for the backside. I've got a drilling operation. Don't need that. I have an adaptive, and I just need one of the contours, right? We just got to change some things. I got to pretend that I'm flipping it over now and think about what's on the back side. The stock dimensions haven't changed. All that's changed is Z. Now that Z's changed, we want to look at it right from the right direction. We'll reverse. It's all really doesn't matter. But you'll see we have a problem. It says there's 0.05 inches when this should be up there, right? We know that there's a lot more stock than that, right? So offset from bottom so it matches the other operation we just completed. And hit check. We just edit it, regenerate the toolpath, boom, adaptive. We just need to make sure we're going down to the right depth, which in this case we already are, so I just regenerate it. Boom, outside, done. And then our contour. This is a problem. We want to make sure we're actually selecting the correct contour, because it's going to try to do that nasty one there. Really, all we do is that, and boom. It's on the outside. There's that arrow I was talking about. It's finally showing up. Yep. And then we want to make sure we go down to the actual depth we're looking for, right? So we just got to select height, bottom, selection, right? I'm going rather quick. Please pause, rewind, etc. And if I want to make sure I'm actually cutting all of the material away in case there's a thin sliver of material, right? I can say minus 0.05. Make sure we get all the material there when we finish it. And then I can do the exact same for the adaptive. I want to make sure we get all of the material, every last bit. Ready? Yep. Minus 0.05. Done. Problem solved. And now, when I run two of these operations concurrently, we'll end up with a final part. And I simulate it. It's going to start on the front. Boom. Stock. We'll go quick. It's going to start on the front. It's going to do it all, and then it's going to flip it over. It faced it. Oops. See, there's an issue there. And something went wrong with the other bit of it. Right, it didn't do that backside. What's wrong? Let's find out. Right, it's going to face. Okay, that's correct. It's going to adaptive. Okay, that's correct. It's going to contour. I'll simulate this and make sure that everything's good there. And sometimes things get glitchy, right? That's the facing operation we want. Oh, I see our problem. We're not taking multiple passes. We're going to take a huge chunk and break the tool. So we want to make sure under passes, because we have more than 0.05 inches, we say multiple depths, 0.05, and hit go. The adaptive something's broken with, it may just need to be regenerated because of the previous operation. Yep, okay. Now let's give it a shot, right? What happens when I simulate both of these together? Right, something went wrong. It didn't do its job. We'll find out what's wrong. Good, it's finishing that side. Finishing pass. Okay, yeah, something glitched with the stock. It is actually cutting, but it's just not simulating properly. So it did that. It doesn't matter. I'll simulate the side. You'll see it'll finish it. Now it's doing it right. Multiple depths, right? It takes a second. Now it's showing up, right? It's doing its job. Finishing operation. And then we're done. That's our part. We can pull it out. It just took 2 operations. You just flip it over and hold it. Make sure you have clearance, and you're done. And so I've just shown you 2 ways to do it, right? Adaptives with 2D and 3D, different selection sets, and then you got to do the backside. You got a facing operation. You have a drilling operation. You always finish adaptives with a contour. You think about what's happening. You watch for errors in your simulation. Stock simulation will just make sure it shows stock, right? It's the same thing as before. So that's how you work in SolidWorks and HSM Works to finish your cam. So I'm going to go ahead and save this to make sure it's here. And we'll talk about post-processing next. But if you guys have questions, hit me up. I want to make sure you guys do this. If you're going to be working on parts in CAM, you should be knowing how to make your own parts, because then when you're an engineer in industry, you can really think about what has to happen. If you design a part with a radius that's really, really tiny, that's going to be utterly pointless. If you design a part with a really, really sharp corner, that can't be machined, right? So you got to think about what's happening when I make this part. In our sense, especially, standardize everything to a decently sized number. If I have to drill a hole and it doesn't matter how big that hole is, pick a quarter 20, quarter 28 if the threads are important. But if it does matter, you can make it something custom, right? But as long as you standardize hole sizes and tooling and all that, it saves us time and money because we don't have access to everything. In an environment like a production run for a big company, they buy the tools for the production run. It doesn't matter. But for us, yeah, it does matter. So think about that as well. Hopefully this has been helpful. I know I talked fast. If it's on YouTube, you should be able to slow it down, cheesy as it sounds. But hopefully this is helpful to get you guys started working in CAM. Thanks for watching. I wish you guys luck. And I'll be available on Slack for questions, and I can WebEx you if you have specific part questions. There'll be videos coming up on how to review parts for manufacturability and then get them approved, and then also on how to post-process when it comes time to machine. Thanks for watching, guys, and I'll see you in later videos.